Good. Okay, thanks. All right, just get back to where I was. Right, so yeah, what is 3D for? Why do we need 3D representations? Why do we need 3D models? Like, why don't we just ask Sora for videos of everything? I think there's a few reasons that maybe we might want to do this, and a lot of them are tied into the just inherent fact that we exist in an ambient 3D world. So, when thinking about things like autonomous vehicles and robots and other things that have to interact with the world, sometimes, it's like you're safe to just do pixels to actions, but in some cases you want maybe not to make the policy work necessarily. You just want some kind of like contractual guarantee that you have sensors that are indicating to you that like, I'm not going to hit a person or a thing or like an animal or a bike if I drive this direction at this velocity for the next 100 milliseconds or something. So in this case, like you actually want the 3D to just take a very basic geometric measurement about the world. And there's other cases that are not to do with like driving or robotics, right? Just like renovating your house or like things like that, where people have these kind of like AR apps where you can take underlying measurements without using a ruler or a tape measure. And all this comes down to just like you want to know rigorous, accurate spatial measurements about the world in a lot of cases. Kind of like the next level up from that, I think, is this idea of like simulating a reality that does not yet physically exist, but that you want to make observations about. So kind of a classic rendering case of this is architectural previs, where you have some nice like CAD architectural diagrams in your computer, and you want to say like, okay, if the sun is here, like if it's this kind of weather or whatever, how is my house going to look? Like, is this going to be nice? Is it going to suck? Is it going to be like blinding me while I'm in the kitchen? Like, how is the kind of flow of light through the room or something like that? And this other famous cases of this, like IKEA, doesn't actually stage the pictures for the catalog anymore. They mostly just have a huge backlog of 3D models that they like set up for each of the different layouts they have. And then they can do this customization like per country, like different cultural stuff really easily without having to actually like painstakingly do this thing in the real world. And of course, like CG for games and movies is a massive industry. And that's all, at the current moment, like all of these tool chains and pipelines are backed by underlying 3D representations, physical simulation, like renderers and things like that. So this is kind of a way of, if you don't want to be like Christopher Nolan or whatever, you can actually film something for not like hundreds of millions of dollars and like a massive amount of physical destruction. You can actually just run this thing as many times as you want and stage it and just burn a bunch of CPU or GPU hours. I think there's also this kind of like other level on top of that, where because people are in like a physical 3D world, they kind of intuitively understand that as an interface for interacting with stuff. This actually doesn't pan out in a lot of, it pans out in two really specific ways, I think. One is games, and then the other one is AR and VR, right? So like AR and VR, there's a reason people find like, hand controllers or like hand gestures and stuff really compelling. And it kind of like immerses you into that medium because it's a much more direct method of control than like dual joysticks, where you kind of like have this unnatural thing you have to learn and pick up and get good at when you're trying to play a game. But even that, I think people find the idea of just being immersed in like some parallel 3D universe to be sufficiently compelling that they're willing to sacrifice the brain plasticity to learn how to like use a second joystick. So I think that's a variety of areas where there is some level of 3D involved in like the current way it's done in software and hardware. I think not all of these necessarily need to be 3D. I think a lot of this like simulation for VFX and other kind of like creative applications, they don't necessarily need that underlying 3D structure guarantee. But in some of these cases, it's really like, it's necessary, right? Like pass through for the Apple headset, like that needs to show you it's kind of a implicit contract with the device that like you're showing me pass through, like I'm not going to walk into a chair that's not there. It needs to be kind of accurate to the world. So this kind of gets to the question of, okay, when are we doing reconstruction? When are we doing generation? When are we kind of like on this sliding continuum between, and when does it matter? And I think I would classify reconstruction at a very high level as, okay, we have a lot of observations or measurements of some underlying signal. Maybe that's abstracted through some forward model, right? Like the classic case here would be you take a 2D picture of a 3D scene, and then you're going to try to invert those to recover some representation of the underlying signal. And here the assumption is like you're actually trying to get the thing that was there, right? You're trying to take enough pictures, enough observations that you can get a reasonable reconstruction and you're not hallucinating too much. As opposed to, I think generation tends to imply that, okay, we're kind of fine with making stuff up that we don't observe. We might have like a purely unconditional generative model, or we might more often want to have some kind of like very loose control, or you might have like a text string or a single image or some other kind of like semantic input that conditions out the full distribution to get us like a sample that we actually care about, right? We have like, I want to do a single image reconstruction, aka generation of like an object or a room, or I want to give a text query and get an input video, an output video from that. And I think something that like you get at a lot with video models versus 3D is this notion that like people have been driving the video models further and further and further. Of course, like Sora is now like clearly the flagship example of this. And it's like kind of like adapting to get a lot of these capabilities that people weren't sure were going to be emergent just with like scaling data and architectures. But it still has like this last level of, okay, if you watch the video for long enough, your brain is like, wait, that is not how that physically could be if I like move the camera in that way. So if you kind of like any individual 1 second clip looks really good. And then if you watch it for like 5, 10, 20, 30 seconds, you start to get these kind of optical spatial illusions that trick your brain a little bit. And I think like I would not go out on a limb and say that this can't be fixed by just like more money, more GPUs, more data. But I do think that it kind of hints at an underlying thing where, okay, even beyond that like baseline level of consistency, there's also the idea of controllability, right? Like, what if I want to change the camera path, or what if I want to like put something in this scene that like respects occlusions that would happen in the physical world? I think those things are places where you might have an advantage in dropping to a more 3D interface. Okay, so that's just some very high level motivation on like 3D, why I continue to be interested in it, why I've been interested in it for a long time. For Nerf, I was coming much more from the reconstruction perspective, but in the last couple of years, I've been getting more and more interested in generative side things. Okay, so what is Nerf? Nerf stands for Neural Radiance Fields. It's a method specifically for the computer vision task of novel view synthesis. So the idea of novel view synthesis is, okay, there's this notion of kind of like regular rendering in graphics. In 3D graphics, we have some like detailed specification of a scene in a computer. We know where everything is. We know like the shapes of things. We know their colors, their materials. We know where the lights are. And we're going to take all of that, process it, simulate a camera looking at the scene, like trace a bunch of rays or rasterize a bunch of polygons, and get out a single output image that hopefully looks, like we wanted it to. And this was kind of one of the like classic motivating examples of the Cornell box, I think from the 80s or something, where these researchers at Cornell like physically built this box and put a light on top of it and took a picture of it with a CCD, I guess, a CCD digital camera at the time. And then they said, okay, can we go and manually specify, like, in the 3D Euclidean space in the computer, where all these walls are, what their colors are, like where the light was, and then run some kind of rendering algorithm such that we can kind of pass this visual Turing test of making the image on the right look like the image on the left. And I think at the time they were like, okay, we did it. The next couple, 3 decades of computer graphics research was basically like this, but for more and more complicated things, right? And I think somewhat in like maybe the mid 2000s-ish, that essentially saturated, and people were pretty much happy with the state of photorealistic rendering, and it started to kind of like roll into production in the next like 20 years until now. And I think a lot of you may have noticed ray tracing emerging as this like really big paradigm in games and in video graphics cards over the last like, 5 or so years. There was kind of a parallel rollout of that in the 5 years before with the movie and VFX industry. Actually, it took, a good decade or so after a lot of these ray tracing algorithms were introduced for them to actually make it into film production because of just like costs and research tech debt and all this stuff, and like things that work in theory for like a couple of SIGGRAPH paper figures, but not that robustly in practice for all the stuff people want to simulate in movies. But we're now at the state where like you can do this for like pretty much anything you specify by hand as a CG scene if you have like a team of 3D artists working for many hours to create sufficiently detailed assets. So the motivating force behind basically all of my research, like through my PhD and until now, is this idea of, okay, that's actually really hard and really expensive. And if you try to learn Blender and like model a scene, it's very painful. And you have to watch a bunch of YouTube tutorials about donuts and all this stuff. So the idea is like, okay, and at the end of that, like you still kind of have this uncanny valley thing, right? You're still not really capturing the full richness of a real world scene, especially like, even one as simple as this. On its surface, right, this is just like, there's like a road, there's like a a thing like a wall in the background with some graffiti, and there's this motorcycle. But like that is an incredibly rich and detailed scene, actually, right? The motorcycle itself would be this like really expensive CG asset if you modeled it properly. Even just getting like a nice texture and the right material on the ground here, this is all very challenging. So the idea is like, okay, how can I, as like a layperson, go and essentially get a 3D capture of the scene that lets us render novel views of it without needing to do any of that behind the scenes work by hand, just by some like automated 3D reconstruction process. And in particular with view synthesis, there's a very specific focus on having very high quality output images. You're not necessarily caring about like, okay, is the like geometric metric accuracy of this reconstruction super precise? Are we going to get like exact material properties out? All you care about like is PSNR and like LPIPs and stuff. Essentially, you want to see like, do these images look really good? And you know, we spent the next 5 or so years after Nerf, like or 4 years, scaling this thing up to work on larger and larger scenes. So that actually was a video. The previous one was not even a video of Nerf. It was a paper before Nerf. And then this is a output from Zip Nerf from like a year or a year and a half ago. This is John capturing his house and then the fly through of his house that we made afterward using the Zip Nerf algorithm. So, you know, this is basically him taking random photos and then we spline a nice camera path through it at the end to get this kind of like cinematic video. Yeah, like I said, so if we wanted to do like a proper computer graphics path tracing rendering of the scene, we would actually need a full decomposition of the geometry, the materials, the lighting. But we specifically in view synthesis just boil this down to a much easier problem of saying like, we only want to move the camera. Everything else can stay the same. We want to move the camera and see like kind of the correct occlusion effects, see the correct reflectance effects. So you see like, you know, the reflection off the puddle in the background there, and that should be correctly preserved. Okay, so that's the motivating problem statement behind Nerf and like other work we did in this area before. Nerf was it was an ECCV 2020 paper. It was like the last thing we did before COVID, essentially. It was me, Pertul, and Matt jointly working together in Ren's group at the time. Me and Matt graduated pretty much right after that, and I think Matt just finished a year ago, roughly. And then me and Pertul ended up joining John's group at Google for the next couple of years until I just left. And Ren has actually gone on to do a lot of work on human vision. His new group is really focused on like kind of retinal scanning and things like that. Okay, so first I'll give this very high level overview of the pipeline, and then I'll get into the kind of like mathematical details behind some of the specifics. So yeah, this is like our like pipeline figure from the original paper. This is depicting the process of rendering out a view from a Nerf representation in the process of training and reconstructing the scene. So the idea here is like, okay, like I said, you have a bunch of captured input images of the scene, and you want to take those to derive some 3D reconstruction that lets you render new views. You actually assume that you have not only those input images, but also their camera pose, extrinsics, and intrinsics. This is like with a ton of caveats, a sort of thing you can assume as solved. Like this is the thing a lot of papers are written assuming this is like given to you. The kind of like under the rug truth of that is like, if the scene doesn't pose, we throw it away and we get a new one. So I would say if you are familiar with capturing scenes in a way that lets them be posed, you can get basically like a 95% success rate, but this is not yet solved to the extent like someone could go and pose every video on YouTube. There's like a big difference between intentional capture for reconstruction and like posing video in the wild. But like, okay, let's say you can run CalMap or some SLAM thing and you could get your calibrated cameras. So once you have that, now you have essentially like a bunch of cameras and a bunch of images and like an empty scene in the middle. So the idea is like, we're going to pick random pixels in the observed images, and we're going to trace those rays out from the cameras just using, standard 3D computer vision geometry. And we sample points through the bounded volume of the scene. Along each ray, we take those points, we pass them through some 3D representation that's going to give us an output color value and an output opacity value, which essentially represents the geometry of the scene, right? This opacity over the course of conversions essentially goes from like kind of like transparent and mushy to something that's pretty binarized to like either 0 or 1. So you're kind of like marching along the ray. Each point along the ray, you ask, okay, is there a shape here? And if there is, what color is it? And after you get all those values, you use volume rendering or alpha compositing to compute the final color per ray. So you say, okay, for all of the samples along this ray, what was the color and opacity? Composite that back to front, get some output value. And then you compare that to what the ground truth value was in the observed images. So if you take, like pixel 2, 3, 4, 5, 6, 7 from training image number 7, you render that ray, and then you just take an L2 loss on what the output, like synthetic Nerf rendered color was. And you do gradient descent on that for like a few thousand iterations with random batches of pixels each time. And you can actually reconstruct pretty detailed synthetic objects in the case of the original paper, and these kind of restricted forward-facing scenes, as we call them, where we did kind of like a window-style capture of the camera only facing in one direction. We ended up lifting, or us and many other people lifted this restriction later, but at the time this was kind of like a compromise to keep the scene in a relatively bounded volume. Okay, so now I'll get into the kind of underlying rendering equation that governs this process of actually taking the output density and color and converting them into a final 2D value for each pixel in the image. Okay, yeah, so I think a good high level like 3-word summary of Nerf is that it's a neural volumetric rendering method. And in particular, I think rendering here implies that like there is an underlying 2D representation. Neural implies that we use this like sort of learned MLP scene representation, and volumetric implies that we're specifically not using a surface rendering model, which was kind of one of the main points of distinction. And each of these things, I'll go over this again later, but like each of these aspects was not a thing that like Nerf proposed in any way, right? Like basically it all existed for decades. But we just sort of unified them and showed that you would achieve very good 3D reconstruction view synthesis results by putting these elements together. And in particular, the volumetric rendering is something where like there's kind of this backstory of I think around 2015 to 2020, people were doing a lot of work to figure out ways you could differentiably render hard surfaces. Like people would blur them in 2D space, they would blur them in 3D space, they do all this kind of stuff to approximate getting a gradient, because it's just this fundamental issue that if you're rendering a hard surface, you either hit the surface or you don't hit the surface. And that is discontinuous and does not technically have like a derivative. You have to rely on the fact that like, oh, I'm integrating over like a pixel footprint, and that gives us like a smoothed out version of the rendering or these other things. Versus volume rendering just very naturally has a trivial derivative if you just implement it in, TensorFlow, PyTorch, whatever. And the difference here is like, okay, with surface rendering, actually this is an implementational detail. In surface rendering, you end up kind of looping over every discrete piece of geometry in the surface, and you check whether or not that hits the ray. So you say like for every triangle in this bunny, is that going to occlude the ray or is the ray going to miss it? And in contrast to that, for volume rendering, you do this kind of like ray first loop where you take these samples along the ray, and for each of those, you just directly query like, is there geometry here, is there not? And you can tell like immediately there's a clear like complexity-wise disadvantage to doing the loop along the ray, because you're obviously traversing a ton of empty space. But it turns out I think that's actually one of the key things that lets the gradient descent-based optimization work so well with volume rendering, because you don't know a priori where the surface is. And the problem with like initializing a surface rendering algorithm is like you have to put it somewhere. So you put like a sphere, some proxy geometry, and that has to kind of like work its way from the wrong place to the right place. Whereas with volume rendering, especially if you have like an MLP or a grid-based representation, you can just instantiate density wherever you want along the ray. And then the game of this is kind of like, okay, once the thing has started to converge, let's find a way to skip all this like garbage empty space that we're needlessly oversampling over time, and kind of have this like multi-phase optimization where you like cut that stuff out. Okay, so where does this whole concept come from? It actually was borrowed from like very, standard radiative transfer physics. I think there's like some story of like Pat Hanrahan has this like his bedside table when he's like working on volume rendering in the 90s. But yeah, people in the very, very early days of graphics, like in the 70s, 80s, 90s, already were doing stuff like this and rendering these partially transparent 3D volumetric objects. And this very quickly turned into like a pretty rigorous physical theory for being able to render like all of these phenomena, absorption by like black smoke, emission by like a flame, and outscattering and inscattering you get from like little water particles and things like that in clouds. People also, not only for this like kind of idea of 3D volume rendering, people borrowed this idea of alpha compositing and like the alpha compositing algebra for doing digital compositing in VFX movie production. So this like let people now say, okay, I'm not going to have to render everything at once. I'm going to split the scene into layers. I'm going to render them. I'm just going to like paste them on top of each other using these alpha layers at the end of the day, which like makes the production process a little more clean and easy. And then the very similar volume rendering model as the one used in Nerf was actually used for a lot of 3D medical data visualization, starting in the 90s with like Mark Lavoie's group and others. So people realize like we have this data from CT, from MRI, where there's not like a great way to visualize it, except like we can do slices, or we can kind of like look at it projected like from the outside, but it's actually very convenient to take these kind of density scans, like, the amount of whatever water the MRI is measuring, and just convert that into a volumetric density field for rendering. People also went through a phase like around 10 or 15 years ago of thinking, maybe we should convert every surface we have into a volume. People were saying like, oh, there's this nice stuff with like grid-based structures where we can do pre-filtering really easily, right? Triangle meshes are very hard to pre-filter because they're not regular data structures. They exist on this like irregular set of points. But a grid, you can go and you can say, I'm going to filter like every 3x3 block of this underlying explicit grid. So there was a moment where people showed that like, yeah, you can actually basically approximate any surface as a discretized volume that's just, like very opaque or has like surface normals, and do regular shading on that. Okay, so getting into the actual functions here. For Nerf specifically, we kick out the really expensive part of volume rendering, which is scattering. So we assume the ray goes through the volume. It's just going to go in that direction in a straight line. It's not going to like turn. It's not going to bounce. It's not going to hit anything else, which is very convenient because then we don't have this kind of like arbitrarily long, like 1,000 bounce path you can get when you're doing full like fluffy white cloud rendering with the sun illuminating it. So this is basically, in physics, I think it would potentially be physically plausible to instantiate a Nerf as some kind of like black body cloud of particles, but it would never actually occur in nature. So you're never going to see one of these things in the wild. But yeah, the things that happen here are basically particles block a little bit of the light from behind them, and they emit a little bit of light in the direction of the camera along the ray. And that leads us to this like probabilistic infinitesimal interpretation of what's going on. So we assume like every little like differential volume in space is filled with tiny colored particles of some density. And then our job is to say like, okay, if a ray travels through that cloud of particles, where is it probably going to stop in expectation of what color are we going to see? So, okay, we want to know basically the distribution over T along the ray so that we can take an expected value over the colors being emitted by the cloud. And then return that back to the camera. And yeah, unlike surface rendering, this is a kind of a soft probabilistic notion. We assume that we have like the ground truth thing that we're given to describe the geometry of the scene is the per volume unit density of particles at each point. And then if we scale that by a differential length along the ray, that actually gives us a proper probability, like the chance that we would stop exactly while traversing that tiny differential dt through the volume. So the problem here is, okay, we know the probability that we stop there, but what's the probability we actually get to that point along the ray, right? So we may have arrived at that point and I want to know what's going to happen, but what about like the rest of the volume that might have blocked us beforehand? So the idea here is that like we want to be able to turn that volume density sigma into this other function, capital T for transmittance, that tells us, okay, what's the probability we didn't hit anything before we got to this little volume we're looking at now. So we combine these two things, we get an actual PDF essentially. We're combining the probability that we didn't hit any of the particles before T with the probability we stop exactly at T. And that gives us T sigma dt here. And you can actually just set up a simple differential equation to solve for T given sigma because of this fact. So we can write this out in exactly that same way, convert it into equations here. So the key fact here is that if we actually didn't hit something in the little differential volume at dt, that multiplicatively combines with the previous capital T to give us T of d plus dt, little t. Because if we don't hit something, then we keep traversing the volume, and then we want to know, do we stop at the place, T plus dt. So we can just write this out here, and then if we use like a linear approximation to expand that 1 minus sigma dt, a linear approximation to expand T of little t plus T dt. This is not made for English language. Then we can rearrange, solve. We just get a very familiar equation for log of x. And that shows us that we get this exponential property that tells us, okay, the probability that we make it to that point t in the first place is just this like negative exponentiated integral of all the density we would have passed through beforehand. And something kind of increasingly interesting in the year since we did Nerf is that this is actually a score function, which people care about a lot more these days. Because we see here, if we just flip that back to write sigma in terms of t, it's actually the instantaneous gradient of the log of that transmittance property. And this is something that shows like, there's always this kind of question of like, okay, what if we have this unbounded sigma field and we do this like exponential function on it, why does that give us this like proper PDF and CDF? This kind of relates those facts and explains that. Okay, so if we combine the equation we got for capital T with sigma, we get the full PDF along the ray. And then all we want to do with Nerf is return the expected value of the color field integrated against that PDF. But the problem here is, okay, capital T actually has another integral hiding inside it that we just solved for. So the problem is like, we can't just do naive quadrature or like we chop this thing up and we say we can evaluate each point approximately, because each of those points we need to evaluate, we're still gonna have to go evaluate capital T. So the way we do this is, okay, we actually do proper quadrature on the inner nested integral with an assumption that each of these segments has constant density and color. And then we do an integral on top of the the inner integral to find the final expression for the approximate sum here. Okay, so this means that we split the ray up into a bunch of little segments, and then we assume we have a constant sample from each of these. In practice, this means like, okay, you sample a bunch of points along the ray, you send them through whatever your underlying scene representation is, and you say, okay, we're going to use that value at a single point as an approximation for the value in the entire interval. And this means we can break up this integral into a series of sums over each of those piecewise constant segments. And for each of the piecewise constant parts of the volume, we do actually evaluate the proper integral with a nested part here. Because you need to essentially account for, if you have like a long interval going through a very dense part of the volume, the transmittance actually is going to fall to 0. Like that interval itself is just going to include the entire thing. I mean, you need to account for that, or else you get like an unbounded sum above in your approximation. Right, so that's the idea of like, okay, if you have this very like dark, smoky interval, you're going to not see anything by the time you get to the end of it. And this goes back to the fact that, again, we can break up T as the product of two things, because the chance you don't hit anything through this part and the chance you don't hit anything through this part are actually just independent probability events. So we can multiply them. And that gives us this, we get this expression for, okay, how much light was blocked by all the previous segments until we got to this one, and then how much light is blocked partway through the current segment. So because we have this approximation for sigma as piecewise constant, this thing is analytically tractable, and it is just this expression here based on the distance we traverse through the interval. Okay, so we substitute that in here. We evaluate that second level of integration. And this is where kind of a mysterious thing happens here, where these sigmas actually cancel out in the numerator and the denominator. And a lot of people get confused here because you have this like the top left equation where there's a capital T and there's a sigma, and then that sigma disappears in the final quadrature estimate. And that's because of this like fact that we accounted for the partial occlusion within each interval. Because if you did just like a direct estimate of this, it would be T times sigma times C evaluated discretely along the ray. And because sigma can be arbitrarily large, that's actually a really bad thing to do, because you would have sigma of like 100 with a sufficiently long interval, and you'll get like a way off estimate for the final color. So this 1 minus exponential of minus sigma times delta is obviously bounded below at bounded above and below by 0 and 1, because we know sigma is always positive. So that works out better. And this is very cleanly connected to the idea of alpha compositing. If we just relabel each of these 1 minus x terms as alpha, then you get exactly the standard thing that you would see in like, Photoshop or Illustrator if you're compositing layers on top of each other with alphas, which is really nice. And then, yeah, so this is everything written up in one place. The key thing here is that like all of this stuff is just smooth functions, right? Like none of these things are non-differentiable in terms of the underlying C and sigma fields. So if we just implement this thing, then it's trivially optimizable in any autodiff framework that we want. Something else that's really nice with this connection to alpha compositing is that it's associative along array. So you can actually like pre-composite together this chunk of the blue cloud and that chunk of the green cloud, keep them as separate image layers, and then alpha composite them in 2D space after the fact. And this lets you do things like, you know, in original Nerf, I had this like really dumb video of a ball like moving through a scene to demonstrate we had actual 3D. And I do this by just like, I alpha composite everything in front of the ball, everything behind the ball, and I like stick the ball layer inside as a synthetic thing. And yeah, you also get like with these Dream Fusion outputs, they exist like volumetrically in 3D, so you can trivially like just, you know, compose them into a scene and render that together with correct occlusions observed. Another thing about this equation is that the interpreting it as the expectation of color over this underlying PDF is very useful because it makes you think, okay, what other quantities would it be interesting to take the expectation over? And we often refer to these things as like the rendering weights, write them like W in papers and code, because like these things are just super, super useful. You can swap in like a feature vector, you can swap in like a distance. It doesn't have to be color that you're integrating against. There's also an interesting aspect here where like sigma is this nice scalar field property, but this PDF of t times sigma is not, right? This is not just a 3D function. It's actually a 5D function essentially, because it cares which direction you're looking, right? The direction you integrate along the ray means that like you actually see the correct occlusion on different size of objects, even though you just had this like underlying 3D field defining the PDF given array. And yeah, like I said, you can use this distribution for whatever you want. The way we got depth map visualizations out of original Nerf was taking expected distance along the ray, so substitute t distance along the ray instead of c. Later we ended up deciding like, oh, we maybe like median or like the top end modes better because you kind of see like the peaks better in the weight distribution. That's something interesting where like at grazing angles, because Nerf is still volumetric, you can get this kind of cloudy halo effect around things, especially when it's reconstructing stuff at such high accuracy that it's like modeling this effect happening in the real world. Because, you know, with a camera, like if you have a mixed pixel that's like looking directly at an occlusion boundary, it's doing an integral over some footprint. So you do get a mixture of the background and the foreground color. You kind of get a similar thing with Nerf where it does like a partial opacity halo at the edge of things to model that pre-filtering effect. So yeah, you don't want to get that in the actual depth maps because you want the depth to correspond to a real point on the scene. So that's one reason to take like the median or the mode instead of just the mean. Yeah, and like I said, we can do this also with feature vectors. People have used this to distill things like clip or dino features into a 3D field on top of the Nerf geometry, as well as just color. And then you get this persistent 3D field that you can query, and you get like a segmentation that exists actually in 3D instead of being like a per image frame thing. So it's perfectly consistent as you change the camera viewpoint. The other interesting interpretation of density is that you can actually take the gradient being like, you know, the direction of steepest change of the density field, and you can treat that as a normal vector that defines a surface. And people often do this to get like normals out of Nerf because the way the geometry evolves over gradient descent is that you actually kind of get it converging to like have a very, very sharp transition, and that often aligns with the perpendicular direction of the surface pretty nicely. So I think this might have had like a little bit of extra regularization to encourage it to get better normal vectors on top. Okay, so that's volume rendering. And now I wanted to talk a bit about the underlying scene representation. So the volume rendering stuff is like, that's mostly just like math. That's a thing that still like exists. The scene representation is a little bit more of an opinionated matter where like this has been fluctuating a lot since like original Nerf and NMLP and like follow-up stuff explored all kinds of different representations. And, you know, of course now there's like Gaussians and things like that. But I'll get a little bit into the motivation behind how we set this up in original Nerf and why that worked as it did. Okay, so this is the neural aspect of calling this, you know, neural volumetric rendering. So the idea here, this is something that really came into vogue in like 2019 roughly, with like Deep SDF and other works that did a similar thing. There was a couple examples of people doing this earlier, but it was really this kind of like toy thing. Like I think there's a Hardmar blog post about it and some other like small papers exploring the idea of representing images inside neural networks and things like that. But it's kind of a mindset shift that beyond the idea that like a neural network takes in a sophisticated high dimensional sample of data and produces some inference about it. This is the idea that like the thing that goes into this network is super dumb, right? It's a 2D or 3D coordinate. And then the thing we're getting out of it is complex, but only in aggregate, right? So we have to basically brute force evaluate this thing densely over many, many 3D points to get out the actual shape that it encodes. The input and output at a single point is almost meaningless, right? It's like XYZ to a single color and a single density value. Locally, it doesn't tell you anything. It's only holistically through like the entire set of weights and all the input and output domain that you actually get something interesting here. And in the case of Nerf, it's one shape, right? So like you start this thing from scratch, random initialization of the weights every single time you're optimizing it for a new scene, which is another thing that's like kind of hard to, a mindset shift to like get people to understand in the context of showing them a network. People expect like big data set, generalization, and so on and so forth. But like, this is more like, it's like a triangle mesh, essentially, the purpose it's serving here. Yeah, so this is a Matt's animation of, yeah, you put a point in, you get some geometric information out. If you query it a ton of times, then you kind of get information about the entire shape. Yeah. Ta-da. All right. So yeah, like I said, this was kind of a thing that it popped up all over the place. I think pretty much concurrently across occupancy networks, DeepSDF, a few other papers. There's one at Nerf at the same time. A bunch of people had this idea of like, hey, let's see what happens if we try to encode geometric shape information into a neural network. It's like, you know, you can interpret it as like, oh, the neural network is giving you like the decision level set of like, am I inside or outside the shape in 3D? And one thing common to most of these works is that they were actually focused on generalization more than like this single shape reconstruction task. Like often they would show like one toy motivating example of like, oh, we baked the Stanford bunny into this network, but then like what they really care about is baking like every shape net car into the network. So this idea was like already in the air that you should consider doing this for like a single scene at a time, but it was not really treated as like a serious endeavor. Like it could get you anything beyond like a more proper method. And I think one of the reasons there was that these MLPs at the time like really were very bad at representing the higher frequency components of the functions that they were trying to optimize. So something we saw here was like, okay, forget Nerf, forget 3D. What if we just go back to a 2D image and we try to solve for a network that maps from pixel coordinates to output colors? In this case, excuse me. In this case, with a vanilla MLP, you get something like this, which is really annoying because this network has more parameters than there are actual pixels in the image. So why is this thing so bad? Like we spent a couple of weeks, like initially in the beginning stages of Nerf, kind of dealing with this like really annoying blurriness effect where we're saying like, okay, this thing, everyone's been telling me MLPs are a universal function approximator for like 10 years, but like that's clearly not a very good function approximator. It's like, what's going on? And the thing we found here, sort of empirically at first, was we were kind of just like thinking, okay, we're essentially putting a 2D, very low frequency mesh grid through this MLP and expecting to get out a very high frequency signal, this like picture of a wolf or whatever. And that's like putting this like, you know, very slow moving coordinate through this network and expecting to get out like an arbitrary waveform or something in 1D. So the idea here was like, let's just give the network more frequencies. Like it still can be this analytic thing that's like known deterministic mapping, but let's just help the network out, like boost its Lipschitz, makes its gradients a little crazier by giving it like a more faster varying signal. And if you do this, basically just put every the mesh grid coordinates through a bunch of sines and cosines of increasing frequency, you actually get this thing to converge essentially like instantly compared to what it was doing before. And it turns out there's a bunch of like underlying theory here sort of explaining that networks themselves are biased to very, very low frequency components of the inputs. And but you can actually just manipulate that by giving them these higher frequencies to work with. Okay, these are Matt's slides. He has like a very nice high level like philosophical interpretation of why this might be the case here. So, okay, if we think about two 2D Euclidean points that we're putting through a network here, they're right next to each other. The image can have an arbitrarily high frequency change, right? You can go from black to white or like across an occlusion edge here, white to red when it hits this triangle. But the two inputs are essentially indistinguishable. Like if you color map them, you basically can't see the difference with your eyes. So okay, it's no surprise that the network can't do this either. you can make some argument like, oh, okay, the ReLU is allowed to have some discontinuities, like you can kind of fit those to the thing, but it turns out it's just like there's not enough like ReLUs to kind of piece together to fit every single pixel in a high frequency image correctly. So the idea here is like, if we provide these positional encoding components, even a small shift, if you map it through a sufficiently high frequency sinusoid, you actually can very easily distinguish between these 2 points. The low frequency components look very similar, but the high frequency component changes a lot. It's kind of almost like feeding the float representation of the number, or like, a fixed point representation of the number through as a one-hot vector. You're like giving it these components that fluctuate way more quickly as you move through space than just like the raw floating point values themselves. And you get these very like nice behaviors here where, so okay, this is just showing if you scale up the maximum frequency of the sinusoid you apply to the input 2D coordinates and do this image memorization task, you get this very, very clean scaling behavior where like the more frequency components you provide, the better the training loss gets. So this is PSNR, so high is good. So once you hit PSNR of like 45, it's essentially perfect. Like that's like floating point error, like quantization error from the 8-bit image. The interesting thing here is that you also hurt the generalization of the network, generalization using kind of a weird sense here where we're talking about like, okay, if we look at what happens between two of those like discrete grid coordinates corresponding to the center of these pixels, and we see like, what's the function behavior like between the pixels, it gets crazier and crazier as you give it more frequencies. Because essentially, like, if you're giving it frequencies that are way, way higher than the actual like pitch of the pixels in the image, it can way overfit to that signal, and it's basically noise. And it's not going to do anything intelligent if you like try to upsample that image by like 2 or 4x and query it on a denser grid of coordinates. This is showing the output on the left is querying the image at 2x the resolution it was trained supervised on. So you can see that it kind of loses its mind and like starts hallucinating a bunch of crazy stuff in between the pixels as you give it larger and larger frequencies. So there's always this kind of like sweet spot in the middle. In the days where we were still using this positional encoding for a lot of stuff with MLPs, you always have to like kind of roughly tune this thing until you got not over blurring and not overly like sparkly aliasing artifacts from giving it too much to work with. So yeah, this is results we had in the follow-up paper to Nerf that explored this idea of positional encoding more. In Nerf, with the original paper, we were trying to find other tasks we could like squeeze into the original submission to say like, oh, this is so general, it's so cool, you can do this with the low dimensional networks now. We kind of ended up packaging that into a later paper we sent to NeurIPS. There was this Fourier feature paper. And we had a couple of tasks there, which was like, this is encoding the SDF of a shape. So not precisely the same as Nerf, because this is an MLP that maps from points to distance to a surface, given like a ground truth 3D shape, just memorizing it. You can see that you basically, the top thing was like the level of quality you could get with deep SDF or something like that before, but to actually get like normal surface detail, you need this kind of positional encoding to boost the frequency content in the network. Same thing with like, we did a toy MRI task and then like a toy Nerf task to get some metrics for the paper. And this was like, this is actually the original scene we tested this method on in Nerf. And I've kind of been like struggling for weeks with results like the one on the left, where I was thinking like, oh, this MLP thing is pretty cool, but like, it's not really high resolution enough to ever be like state of the art. Like it's cool that this thing is an MLP intellectually, but it's not like actually a useful method. But then you just put in this positional encoding thing and you kind of magically solve all of your problems with essentially no extra compute or memory requirements at all. It's kind of just like a neural network preconditioning thing that just makes conversions much better. So something here, I mentioned like the original Nerf used positional encoding with frequencies that were powers of 2. In the later work, we proposed using like frequencies sampled from a Gaussian distribution or something. You might think, okay, those are just parameters. Let's learn those as well. Why don't we just put those through gradient descent as well as the MLP weights? And the idea here is like, it turns out that like, as soon as you start training this thing, you kind of get the signal evolving in lockstep with that underlying parameterization. Like you can imagine that if you change the frequency, it's tied to the input spatial coordinates in a way that like it essentially scales up and down the shape of the object. So you get this global lock-in effect where like the frequencies maybe can drift a tiny bit at initialization, but then they have this like global dependency on each other, and on the signal being optimized, it means that they just can't move, right? This is Matt's explanation of this, and I was trying to understand what he was implying, but I didn't quite get it. So yeah. Yeah, so the idea here is like, okay, what can we do to make this thing learnable? Maybe we don't have these like global sinusoidal functions anymore. Maybe we actually like chop this up and we have more locally, spatially localized features that we can learn. And the clear solution here is like, okay, let's go back, let's get discretized space. Let's have like, maybe a voxel grid of features that we feed through an MLP to be acting as a learned kind of encoding. And the whole reason we and a lot of other people were looking into this MLP thing in the first place is this like cursive dimensionality in 3D, right? So grids are fine for image. People are now feeling the pain of grids for video, but like it's still sort of okay. And you have like a dense signal to make it be reasonable, but there's really no good justification for having a dense 3D grid sampling shapes in space because they're naturally super sparse, right? Shapes are like this 2D manifold existing in 3D space. So having a dense 3D sampling at high resolution is completely wasteful. And yeah, the way, so back to the encoding thing, the way people made these encodings continuous to use them as similar way to the sinusoids is like, oh, you can actually just feed a trilinear interpolation of these feature vectors through as an encoding. And that turned out to work like very, very well. So this was a paper, like, I don't know, like a year and a half after Nerf. There was a whole set of like 3 papers or 4 papers at the same conference that basically were like, get rid of that big MLP, just use like a 128, 256 cube voxel grid, use trilinear interpolation with a little MLP or some activation function on it. And that actually still gives you like high frequency enough edges that it can work quite well. Right, and so back to the idea of this like wastefulness of the dense 3D grid, there's a couple of different directions people have gone to amortize that fact and reduce it down to like a more manageable scale as you get higher resolution in 3D. And those are basically like different methods of sparsification you can apply to the data. So there's like literal sparsification in which you just greedily optimize, check for empty space, and like cut it out. So you have like your fine grid resolution, and at some coarser resolution, you're gonna like inspect each cube in space, see if there's density there. If there's not, you just say like, this is dead, there's nothing here, I'm never gonna look here again. I'm gonna create some acceleration structure that just marks all of the like coarse empty cubes, skip over them when I'm traversing samples along the way, and only sample from the places where the actual geometry is. People will like iteratively do this over and over again over the course of optimization, like every 5,000 steps, just take a look, check all the non-empty space, see if it's still really non-empty, and then keep track of that over time. People have done others, so that's like a very like discrete heuristic thing that you have to implement yourself and go brute force query for where there's density and where there's not. There's sort of like more intermediate things like these low rank approximations where people will just say, okay, I'm never going to instantiate a dense 3D volume. What I'm going to do is always learn that thing in a factorized low rank representation. So there's like TensorRF and some other related work that did this where they would say, okay, I can like represent a 3D volume as a low rank outer product of like 3 1D vectors, or like maybe a 2D plane and a 1D vector where like I project onto the z-axis and grab a feature, and I project down onto the xy plane and grab another feature, and I like add or multiply them together. And this works pretty nicely. Like the representation here, especially this representation from the EG3D paper called a triplane, has really persisted through a lot of the generative work because it's this nice like clean representation for a 3D volume based on a set of 2D feature planes, which you can just glue into a bunch of like existing image generation architectures. Another interesting method is these things called like a dictionary method. So, okay, well, instant NGP is kind of like one of the most well-known like Nerf follow-ups that basically got the training time for these synthetic scenes down to like a second or two from the original day or two that it took us with the MLPs. And the way they did this was they basically outsourced all of the work of the MLP to this underlying spatial hash grid. And they got around the resolution issue by saying like, okay, space is sparse, so we can use like a really aggressive hash function that just maps a ton of points to collide with each other in space. And most of them won't hit the surface. So the collision will kind of naturally resolve itself. And we're using gradient descent, so it will also resolve itself just through like learning and optimization, right? We'll sort of like let the thing figure itself out. We're going to give it this hash function mapping, and it can like use these features to store stuff spatially as it will, and resolve the collisions just by like the way that best optimizes re-rendering loss. Yeah, and one thing all of these have in common is like they actually ends up still usually being a small MLP at the end of the day. So in particular, when people want to represent outgoing like view dependent appearance as a function of ray direction, they'll like feed that signal through the MLP along with a feature. Or if you want to have some like appearance encoding vector or something like that, people will just take this like spatial memory bank, use it to grab a feature, concatenate that with other interesting information, and then feed that through a small MLP. Yeah, and like there's, I guess, it's kind of just like oscillating like tide of research, thinking like, okay, so for a while we thought voxels are untenable, we can't use them, like it's not going to work. And then it turned out like after we tried the MLPs, voxels are still not so bad as long as we sort of sparsify them very aggressively or use one of these learned sparsification structures. So it got to the point where there's sort of like, takedown papers like, you don't need an MLP after all, like, gotcha. But it's like, okay, sure. Like the underlying like framework is still basically the same of this like single CM optimization with the volumetric rendering model. And like, yeah, it's not super surprising that we can find other ways to represent this signal spatially. And yeah, it's sort of like everyone's still like going in this kind of spiral of like trying different representations and different combinations for different tasks. There's obviously a big difference between tasks where like you're just doing a pure optimization loop to render a single scene versus things where like I want to output something 3D from a feed-forward network. Those lend themselves to like totally different representations. But there's still kind of like not consensus on either side of like which one of these things is really going to work. And like that's been most clearly demonstrated over the last year by like the Gaussian stuff, right? Everything that's been done has been rewritten in a Gaussian version by now. And it's going to be really interesting to see like, okay, where does this thing end up going? Like there's a bunch of very clear advantages to that where like you have actual discrete particles representing the geometry we've seen. You can use rasterization and so on and so forth. But there's kind of like this classic like Euclidean Lagrangian trade-off of like when do you want a grid, but when do you want like explicit particles? It's been playing itself out in like physical simulation world for decades. And I expect to see a lot of like similar back and forth and like, okay, when do we want to have a structured output on a grid? When do we want to have this like loose kind of collection of particles? Okay, so yeah, back to the original Nerf results. Yeah, so yeah, this is the original Nerf paper again with this like 8-layer MLP, volume rendering, view-dependent effects. We rendered this synthetic data set of objects from, I think, like blend swap or turbo squid meshes, because at the time there wasn't really a proper view synthesis data set for these challenging type of objects where there's like very complex geometry and there's specular reflections. I think by this point, performance is mostly saturated on this data set. We rendered out 100 views of each of these objects. We actually originally rendered 400, thought that sounded not impressive enough, so we went down to 100. And these days, I think like, PSNR is like 35 or something, like people should probably stop using these essentially. But at the time, it was a big step up above the complexity of the previous data sets. Yeah, we also had these kind of like forward-facing tasks, which people surprisingly do sometimes still use. This was mostly just an issue of like, how are we going to handle unbounded space? In original Nerf, we actually just had like a method to compress essentially like a forward-facing volume into a single cube by using like a 1/z mapping. So that's why we focus on this kind of scene. We had a couple of these very carefully staged like 360 renderings, but this actually relies on the fact that the camera is pointed down toward the object in such a way that you don't see the horizon. Like if you keep looking farther away from this object, you actually end up seeing that like the horizon is a total mess in these cases, and only the object and its immediate surroundings are constructed cleanly. Okay. So yeah, given that summary of the stuff underlying original Nerf, I kind of made a takeaway slide talking about like, okay, which of these things are still like reasonable conclusions, and which of these are like totally outdated at this point. I think it's interesting to look at these 4 attributes, where one is the MLP for shape, like I talked about in the representation section. And the other I didn't talk about quite as much, like this idea that we were encapsulating view-dependent appearance as part of the MLP function mapping. The idea of doing this optimization over a single scene at once instead of trying to generalize, and the idea, of course, I talked a lot about the volume rendering equation. And yeah, like I said, none of this is proposed by Nerf at all. It was just kind of like united to solid performance in the original paper we did. I think, yeah, MLPs for shape is kind of dumb at the end of the day. Like it's intellectually curious that an MLP can do this, but I think very impractical essentially. The only extent to which it's really interesting is like the MLP is actually a very compact shape representation. It's like 5 megabytes in original Nerf compared to most of the discretized equivalents you might have. There's a kind of like higher level, like deep learning takeaway thing here, in that MLPs are actually really good regularizers for low dimensional spatial signals. So people have started exploiting this. Like I've seen, you might think like MLP for spatial signal, it's done, like no one's going to do that anymore. But people have adopted it quite a lot for these deformation and tracking based work. So even if maybe like the underlying scene representation is still a grid in like this deformable Nerf or something, the idea of using an MLP to track like, okay, from time t to time t plus 1, like where does this point move? That actually has a very like low frequency spatial signature that maps very well onto the kind of smoothness that an MLP imposes on the reconstructed signal it encodes. And we actually already kind of knew that because of deep image prior and similar works where people have observed, like, if you take a UNet, you feed random noise into it, and you optimize it to reconstruct a single image. Like I just take the noisy image on the left, I use that as the L2 loss target for a UNet, like no other images at all, no input besides noise. You actually get this effectively like denoise version of the image. And they showed that you could do this for like in painting and super resolution, other kind of similar tasks. So this phenomenon of like the empirical smoothness regularization of MLP had already been investigated quite a bit. And we were kind of like still like repeatedly amazed ourselves at like, why isn't this thing just like, why isn't there a bunch of garbage floating around in the scene? Because we had tried doing direct voxel grid optimization before we tried the MLP stuff. And you always get these kind of like fuzzy clouds and these things, annoying things like floating around. But the MLP just has like the precise right amount of capacity and smoothness to represent these signals in a convenient way. And yeah, like I said before, it's quite a compact signal representation. In the case of memorizing an image, like I was showing with the Fox image, you actually can't really make the network weight small enough to represent that image decently and have it compete with like a JPEG or something. But something funny that we realized a lot was like with a Nerf, like the MLP weights would be smaller than the MP4 renderings we baked out from the Nerf. Like this was actually a pretty compact representation of the scene. Yeah, and with again with image and video, like the codecs you use to compress it are like very, very precisely engineered by people. They work really well. They're like designed for human perception, but they're not natively differentiable, which is the problem, right? So like if you want to recover a naturally sparse signal and you never want to instantiate the uncompressed version of it. So like you have this dense 3D signal and like I can never afford to make, a like 4,000 cubed volume. Maybe on like an H100 now you could, but not on 8 gigabytes or whatever. So you want to be like, I need this thing to kind of be differentiably compressed while I'm optimizing it. MLPs serve really well to do that. But yeah, once you kind of get the final output, it still makes sense to like bake it out into a properly compressed format. You can have just like a empty space skipping structure, like densely query the thing. Shipping the MLP as like an actual like file format essentially never makes sense. So yeah, the next thing I wanted to mention was this idea of using an MLP for view dependent appearance. I didn't touch on that much in this version of the talk, but it's still kind of back and forth on this one. Like basically you need a function basis for representing color values on a sphere, and then MLP works about as well as any of the other things people have been trying, and it's more compact than some of them, right? Like spherical harmonics kind of blow up for high frequencies. Spherical Gaussians are fine, but the MLP works quite well. In original Nerf, we would do these like dense queries for a single 3D point in the scene, query all outgoing directions and see, well, how did the color change as you did that? If you do that for an actually shiny object, you get this kind of nice effect of like, oh, I see like a localized white highlight at the grazing angle on the ship and on the water. And it's like the same kind of thing you see with explicit parametrized representations like Gaussians living on a sphere. Okay, yeah. I think this idea of doing like an inverse framework optimization to do single scene 3D reconstruction is really good. And we've seen it proven to scale to ridiculously large scenes. Like doing original Nerf, I would never have expected you could just do the same framework with like a bigger scene representation and more images and get something like this out of it. This is like one of the Google New York cafes, I think. This is from 1,500 images, and it's just a big NGP grid underlying it. The scene representation now balloons to like 200 megabytes, but it's still at the end of the day the same, just like sample random pixels, apply an L2 loss to them, and optimize for 25,000 iterations. And you can get this kind of reconstruction now. And it's really like, it goes against the kind of like feed forward paradigm of like, oh, we want to feed every single input image in and get the thing out wholesale. It's just this like loop of optimization. Yeah.
So I just have like a general like big picture question. So like I think the Nerf is super impressive in terms of just like as a compression technique, how it's able to like capture all this photorealism with like such a small MLP. But like what I'm curious about is like for applications outside of graphics, like for robotics, for example, where you have like very dynamic scenes, like you have to retrain this every time the scene changes. And like I see like neural radiance fields are like very popular in robotics, but I'm also a little bit confused by the popularity because of the lack of dynamics, because my understanding is it's basically overfitting to the scene. Like it just basically learns the exact scene. So it's basically like a very powerful compression technique. So do you think it's possible to ever make this dynamic in like real time in terms of like 20 hertz, 30 hertz, or is that not possible to like train a neural net to update that fast?
Yeah, I mean, in terms of the first consideration of like making it dynamic, there's actually been the huge amount of follow-up work that just will add like a deformation field or the ability to like disentangle components and move them separately. So like that stuff has and especially with the Gaussian stuff now, like it's just a bunch of points. So like you can just freely move stuff around. You can solve for like a tracking like field that keeps things in 3D. So like every object you could imagine disentangling if you have enough observations. In terms of like 20 or 30 hertz, I think that's like another question. Like people have been pushing like for a while they were working on like Nerf type slam things, now Gaussian type slam things that actually can run pretty fast. Those are mostly to map out static scenes. I think like doing this live and keeping track of deformable objects is harder. I have seen actually some results people did with multi-view camera setups where they're all streaming video, where you can kind of like, you take each multi-view step and then you do a pretty quick update of a few steps of gradient descent to just like kind of relocalize where stuff moved or like maybe like reconstruct new things that emerge in the scene. I think it's still like yeah, it's not, it's at like a base level, just like getting this like frozen reconstruction that's compressed of the 3D geometry is not actually that useful. It doesn't even tell you like affordances and like what can move in the scene and things like that. So yeah, I think basically, like you said, you need a lot more data on top that like heuristically disentangles the components or like keeps track of them as they move and things like that.
So in that case, like if it's mostly useful for like static scenes, like you said, then what do you think are like useful downstream applications for this? Like, is it more like AR and VR or like?
Yeah, I think this is not that useful. I think mostly it's useful in that it motivates progress in like other better pipelines that do like deformable stuff or disentangled stuff or things like that. I think like this is basically an academic problem that motivated a lot of improvement in 3D representations and reconstruction in a way that like spread itself out into all those more useful versions of itself, essentially, right? Like I think having this thing baked out, it's like basically it's good for making these fun videos and maybe like selling your house, but like not that useful for other stuff. Yeah, looks fun, but yeah, it's very academic essentially. Yeah, I think that's totally true. Okay.
Thank you.
Yeah, I'm just gonna go through like 4 more slides here. Yeah, so I think on my little self-report card here, I think the final point of this question of volume rendering, I think this is just like proven itself to be a very useful paradigm for doing reconstruction and optimization. We've basically seen most things that like claim they're doing a hard surface optimization these days actually optimize a volume parameterized by the hard surface. Like we see this kind of SDF type things that like convert the SDF into a volume to optimize it. And we just see that like the properties, if you want to start with like no a priori information about where the things in your scene are besides like maybe a bounding box, it converges so cleanly and so fast and so reliably. That it's hard for me to imagine bootstrapping a surface method to work, like especially in a scene like this, right? Like, what are you gonna put like a sphere in the middle of the scene and expect it to blow up to the entire room? Like I think any kind of like surface-based things usually come out as a result of a downstream processing where like you start with a volumetric optimization, then maybe you mesh it and you refine that. So yeah, I think that this volumetric stuff is just really powerful, and that's been like that was already happening basically for like 3 or 4 years before Nerf. We were seeing a bunch of different feed-forward view synthesis methods that were using volumetric reconstruction, and also like single shape 3D generative methods on like very small low-res voxel grids that were using a similar like mathematical formulation. So that was kind of just like a tide that was happening, and it's continued since then. I think this seems like a great stopping point to cut this off. I got through the Nerf slides, no future slides, but